Matschke on the theory of linear programming, but he's a member here. I think you want to say what kind of member you are.
So I was asked to let you know that I'm an EPDI fellow, so I'm here for the whole month. So I'm very happy to have this fellowship. I don't ever. Okay, do you hear me actually?
No.
So is the microphone on? Oh, it's off? No, it's on. Is it better like this?
Oh yeah.
Okay, so I'm very happy to be here, and actually this talk goes back to the roots of actually linear programming, so it's not about semi-definite programming. I hope you don't mind that I will use the blackboard. And it's actually also not about linear programming in this sense, but it's more about polytope theory. It's about diameters of polytopes. So this could have been actually a slightly less precise title, but a title that everybody understands. And this is joined with Paco Santos. And Christoph Weibel. Is this big enough? Yes, okay, very good. And the motivating and very central conjecture in this area is the so-called Hirsch conjecture. And I guess that many of you know what this is, right? But let me still explain what it is. So this is from 1957, and so it was motivated by Danzig's simplex algorithm. It asks, or it conjectures, that any d-dimensional polytope with n facets, so it's given by n linear inequalities, has a diameter, let's call it p, diameter of p at most n minus d. So it would say that if you start the simplex algorithm, you start with one vertex and you try to find the optimal. You walk along the edges. Every edge in this diameter definition basically has length 1. You ask how many steps do you need to go from the starting vertex to the optimal vertex, and well, the diameter is if you start at the bad vertex will be, and if the linear functional is given in the worst case, this will be a lower bound for this running time. Of course, well, if you know that the diameter of a polytope is, if it's small, you don't know whether, or in general, this does not give you a fast algorithm because, well, you still have to find at every vertex basically the best possible way how to continue. But okay, is it clear what the diameter is? So I have here a polytope. It has vertices and edges. This forms the graph, and if every edge has length 1, this is basically the diameter of the resulting metric space. So the largest distance of 2 points that you can find. What? Sorry? D is the dimension. So okay. So in this talk, D will always be the fixed dimension. Later it will be 5, and n is the number of facets. Okay. And let me give you one example. The cube. You can also make it in higher dimensions. You can think about this example in higher dimensions. This has diameter 3, right? Because these two vertices have distance 1, 2, 3, and this is also the maximal distance that you can find between any two vertices. So 3 is the diameter, and it has 6 facets, and it's of dimension 3. In general, in higher dimensions, the cube has n facets, and which is 2 times the dimension, and the diameter in this case is also equal to d. So it fulfills this Hirsch conjecture with equality. And another example, which is maybe even simpler, is the simplex. So if you take the D simplex, it has dimension d. It has d plus 1 vertices and d plus 1 facets, and the diameter is 1. also fulfills this bound with equality. And in general, if you have polytopes that fulfill the Hirsch conjecture, then you can take products, and it will, well, if you take a product of two polytopes, the number of facets, the diameter, and the dimension behave additively. So, and this is just a linear inequality. So taking products will not give you a polytope getting out of this Hirsch conjecture if you start with so-called Hirsch polytopes. But, question? No. So what was known? Well, lower bounds have been quite complicated to find. But what about upper bounds? Actually, I should mention that originally it was asked for polyhedra, so for unbounded, possibly unbounded polytopes, and there Klee and Walkup found a counterexample, but it was not possible somehow, or it was not clear how to make this into a polytope counterexample, but more to this later. So upper bounds, there are basically two of them. So upper bounds on the diameter of polytopes, namely, the first one was due to Barnett, and it was improved by Larman, and then again by Barnett in a series of 3 papers around 1970. So Larman's paper was from exactly 1970. And they say that the diameter is always at most something like 2 to the d times n. Actually, this is proved by induction, and depending on where you start the induction, you can fill in here a constant like 3 over 4 or so. But this constant doesn't really matter. And so this constant holds if the dimension is at least 3. So what is nice about this bound? Well, if you fix your dimension, then it's a linear bound, which is very good. So it's very close to the Hirsch conjecture. But in general, I guess also in practice, the dimension also grows with the number of inequalities. So in this case, it's actually, I guess in practice, it's the worst of the 2 bounds. And here's the second bound. The second bound is due to Carlyle and Kleitman. So Kleitman found this bound, and Carlyle found a very nice way to write this up, the proof. It's from '92. It's a very, very short paper. It's very beautiful. They proved that the diameter is at most n to the log d plus 1. And the logarithm is in base 2. So if d also grows, then this is usually much better. And both bounds are basically proved inductively. So here for the first bound, the idea is basically you take your polytope. These are 2 vertices, say A and B of large distance, and you try to cover some shortest path between A and B with facets, with as few facets as possible, something like this, and you do induction on the facets. And here the induction step is slightly differently. Basically, you try to cut your polytopes into halves, and you try to reach some facet from the one side and also from the other side, and then you do induction, well, on this facet and on this part of the polytope and on this part of the polytope. And, well, I just want to, this is just to say that basically you can put these induction steps together to form a unified bound, but in general, this is actually, I guess, easiest to write down. So it, yeah, probably it doesn't make sense in general to make this more complicated bound explicitly. Well, what about lower bounds? Well, this is actually the topic of this talk. And for this, I want to define what a d-dimensional spindle is. So in the talk announcement, so the title of the talk was The Width of 5 Prismatoids. This is the dual notion of spindles. And I thought that it's probably much easier to talk about spindles. What is a d-spindle? A d-dimensional spindle is a d-polytope So a polytope in dimension D with two distinguished vertices called A and B, such that every facet contains A or B, or both. Okay, so what is an example? Well, in dimension 1, we have only one polytope, and it's a spindle. Where here, this is A, this is B. In dimension 2, there are two cases, a triangle, say A and B are these vertices, and a square. And in dimension 3, there are many examples, but they are also quite easy. So they look like this. Yeah, something like this. And so this is the main notion of this talk, together with the width of this spindle. So call it S. So I define the width, W of S, as the distance between A and B in the graph. Okay, so the distance is the number of edges that I need to travel on the shortest path from A to B.
Where is A and B in this slide?
Yeah, sorry. This is A, and this is B. And so what is the width in these examples? So here, so here the distance is 1, so the width is 1. Here the distance is 1, so the width is 1. Here it's 2. And here it's probably 3. I just draw the front face of this polytope, basically, or the front side, not the back side. And here the width is maybe, I guess, probably 3. But it can be easily also 2 by, for example, breaking this quadrilateral into 2 pieces. So if I make this facet here into 2 triangles, then the width would be 1, 2. Right? Okay, so these are the main notions that I need. And why is this? Why do we care about spindles? The reason is that Paco Santos recently found two very important theorems in this area. Namely, the first one is the following. Oh, do you have a question? You look like okay, very good. So the first theorem of Santos is some induction argument. So this is from 2010, but published in 2012. He proved that suppose you are given suppose you're given a d-dimensional spindle with n facets and width w. Okay, and then assuming that n is larger than 2d, which basically means since every facet has to contain A or B, one of the vertices A or B will not be simple, so it will contain more than d facets. It will be contained in more than d facets. Then there exists a d plus 1 dimensional spindle with n plus 1 facets and with w plus 1. So basically all 3 parameters go up by 1. Yeah, unfortunately I won't have time to tell you how this works. In this setting it's actually much easier to see the construction in the prismatoid world, but for what I will present here, the spindles are really, I think, easier. So this is one theorem which can be used inductively, and the start of the induction is another theorem of Santos from the same paper, namely there exists a 5-dimensional spindle with 48 facets, so n is 48, and W is 6. So the important thing is that he constructed a spindle where the width is larger than the dimension. And whenever you have this, you can apply, so whenever you have a polytope, a spindle, where the width is larger than the dimension, then you can apply this induction step several times until you reach a polytope where n is equal to 2d. Then you stop this induction, and you found a counterexample to the Hirsch conjecture. So using this theorem, so say this is theorem A and this is theorem B. You use theorem A. I think here you use it 38 times. You get a 43-dimensional spindle with width 38, 44, and n is equal to 86. And this was the first known actually the first published counterexample. He had previously slightly more complicated constructions, and it was, I think, some much higher dimensional counterexample. Okay. Are there any questions so far? No. Very good. So it's very interesting to see how far this method can be extended, and so what Santos proved, and independently Stephen and Thomas, and they published this in a common paper. They proved that there exist no there exists no D spindle with width larger than D if the dimension is at most 4. So so this the start of the induction cannot be 4 or less dimensional. So 5 is really the first dimension in which you can find such a spindle that gives rise to a counterexample. So that's why we are now interested in 5 spindles. And basically, we have 2 theorems. The first one is that there exists a 5 spindle with 25 facets, and width is 6. Okay, so it has much less facets, and therefore applying A, I think 15 times, you get a 20-dimensional spindle with 40 vertices, with n is 40, and width is 21. So this gives a much smaller counterexample. And actually, so this counterexample, and this one also is very nice, because from this counterexample you can construct new ones by taking the product with itself a lot of times, because as I said, all 3 quantities, the diameter, the number of facets, and the dimension will grow linearly with the number of factors that I use. So instead of having here a gap of 1, we can make this gap arbitrary, and then if the gap is quite large, then you can start in this dimension to glue this polytope with itself in a reasonable way, such that you can actually deduce the following. There exist there exist polytopes with dimension d, n facets, and width w, with where the diameter is, say this polytop P, where the diameter is 1 plus 1 over 43 times n. This was what Santos proved, and we could make this 43 now into 20, say plus an epsilon, very small epsilon, arbitrary small epsilon. So actually this d is not very important. Whenever you have a counterexample to the Hirsch conjecture, then you can make this into counterexample to such a Hirsch conjecture where you forget about this minus d.
Can you say equal, or is it at least that?
Sorry, minus epsilon.
Oh, okay.
More or less, asymptotically. Yeah, sorry. And for this you also need to make the dimension very large. If you want to have it in a fixed dimension, then this bound will become worse. But well, this is linear, right? It's a linear lower bound. What about, well, the upper bounds are still the ones that you can see there. So there's a really large gap, and we have no idea what the correct bound is, or what the correct upper bound that you can get is. And it's conjectured to be polynomial. This is the polynomial Hirsch conjecture. So it's still about polytopes. It's not about somehow spectrahedra. So actually, I'm not sure what the correct analog of the diameter would be for spectrahedra. This might be interesting for you also, maybe. But of course, spectrahedra are more complicated. So if you can't even solve this, maybe you can find lower bounds for a reasonable definition of a diameter for spectrahedra. I don't know. Maybe with spectrahedra you have much more possibilities to construct something with a large diameter. Okay. Anyways. And what I wanted to mention is that the polynomial Hirsch conjecture was one of the polymath projects. It was the polymath project number 3. So many people collaboratively worked together to find better upper bounds or the correct lower bound for such polytopes. Actually, they used a combinatorial abstraction of polytopes due to Eisenbrand, Hähnle, Rothfuss, and Rasborov, and it seems that it didn't really succeed. So we don't have new upper bounds, but this abstraction is better understood now. But as long as you can't find better upper bounds for the diameter, I think it's unfortunately not that interesting, unfortunately. So this was the main goal with this abstraction. Okay, so now I have, I think, 5 minutes to talk about the construction. So how did we define? I will only talk about. I didn't tell you the second theorem. So this was the first, and the second theorem says that actually there exist 5 spindles with width growing like omega of square root of n. Actually, I can make it more precise, so it will be at least square root of n over 18. I think plus a constant, but it doesn't really matter. So the width of 5 spindles can grow arbitrarily. So it goes to basically, well, it can be arbitrarily large. Whereas for 4 polytopes or for 4 spindles, this does not hold, which is maybe surprising or so. But the higher dimensional polytopes are, the more interesting combinatorial features appear. So already 4-dimensional polytopes are very complicated. So here's a question: does the polynomial does the Hirsch conjecture hold in dimension 4? This is open. So if you can prove the Hirsch conjecture for dimension 4, or find a counterexample, this would be really nice. So far we only know that there's a 20-dimensional counterexample, but does there exist a 19-dimensional or a 4-dimensional counterexample? We don't know. Okay, so how do we construct this spindle? The idea is as follows. So constructing something in 5 dimensions is complicated. But we have something like a spindle which looks maybe like this, right? Well, here's A, here's B. We intersect the spindle with a 4-dimensional hyperplane. So we take the vertex figure of this polytope here, and also the vertex figure here. And if you take the central cone, where the origin should actually lie here on the line between A and B, so that's where you define the origin. You take the central cone of those two, and if you take the common refinement of those central cones, this will give you the central fans. This will be the same as the central fan of the projection of this polytope to R4. When this line connecting A and B is the kernel of this projection. So we basically only need to construct a reasonable intersections here. So we only need to define something 4-dimensional. And actually, what is a 4-dimensional polytope? Well, it has a 3-dimensional boundary, which is nice. Or the central fan can be intersected with a 3-sphere. So we only need to construct something in a 3-dimensional sphere. And how do we do this? S3 is actually the same as S1 join S1. Right? So connect every point from one circle with another circle, and you get the 3-dimensional sphere. It looks like this. So probably, yeah, it looks like this. So if we are here in the 3-dimensional sphere, one point is at infinity, then we have here one circle, closes up at infinity, and here's another circle. Right? Okay, but I like the following picture better. S1 is an edge where you identify the two endpoints. Here's the other S2, and now you just take the join of those, which is a 3-dimensional simplex with some identification. So you identify this and this facet, and this facet. And what we do here, so here's one circle, here's the other circle, and we put the points of one of those polytopes on one of those tori. The square is a torus. So in this picture, maybe this torus looks like such a torus. And we put some other points on this torus. It looks like this maybe. And so how do we put points on here? Well, what time? Okay. Okay. Maybe can I quickly show you an animation or so? And yeah. Do we have 1 minute? I think it's coming. So here are the two tori, and we put points on them. And well, I think I can't explain you the combinatorics, but if you put the points well enough on the torus, then you will have basically 3 kinds of facets. So in every torus you have basically in one torus you have facets that basically are in one of such cross section of the torus, and also in those horizontal cross sections, and well, they have a very nice intersection property. Yeah, sorry, I have no time to explain more, but that's basically it.
Sake of time, we direct the questions to the speaker. We have another speaker coming up, Martin Lotz.